Hello and welcome to Optimization. My name is John Snelson and I'm a Principal Engineer and lead on the Optic Engine team at MarkLogic. This is the second part of a 5-part deep dive into the Optic Engine and how it's implemented under the covers. What that means is that if you have not watched the first part about query plans and of the operators that are in them, you may find it useful to go back and look at that before you watch this part. Because we're going to dive straight into how optimization happens and what kind of choices we're making about those operators in order to get the most optimal query plan to execute it. When the optimizer gets a query plan, if you recall, it gets a logical query plan that contains the what but not the how of how we execute. It goes through several stages as it makes decisions about the best way to execute that plan. So the first stage is static optimization. And everything in static optimization always happens. There's no decision about it. It always happens. So they're always good things to do. Then we do some heuristic optimization, and that has two roles really. It needs to make some rule of thumb changes that are usually better, and it prepares the plan to be better to start cost-based optimization, which is where the real meat of the optimization happens later. And a crucial part of that cost-based optimization is the cost function that gets used to determine whether a plan is considered better or worse than another plan. So we'll look at exactly how that's done as well. So one of the most important things that the static optimization phase does is it pushes down filter expressions. And here we can see a query in the grey box on the bottom right, and that query has a where clause with actually two parts to it. And what we can do is we can split these expressions on the outermost ands and treat each clause separately. And in fact, this query has got two clauses, one of which can be pushed down and the other of which cannot. You can see in the plan here that the green highlighted section of the plan corresponds to the green highlighted section of the query. So what exactly do I mean by pushing down? So when a filter expression is pushed down, it's moved in the query plan towards the leaves of the query plan, towards the index accesses and the data accesses that if it gets attached to an index access, then it's likely that we can perform that index access more efficiently. If it gets attached to a join, then it's likely that it becomes a join condition, and that join becomes more efficient. Often when we push filters down in this way, that means their execution can also be moved to the D node rather than happening on the E node. And that means that it can happen in parallel and be more efficient as well. So what kind of filters, what kind of expressions can be pushed down? There's a fairly small set of conditions that can be pushed down, although that set is getting bigger. So here's a few examples. On the left hand side we've got SQL expressions, and on the right hand side Sparkle expressions, depending on which you're most familiar with. Now the most obvious kind of expression that can be pushed down is column equals column, or column equals expression, where that expression doesn't, that expression may or may not use the value from other columns. And column equals column, or in fact any kind of operator instead of equals, any of those operators along the bottom there of the screen, that will usually get turned into a join condition. Often those columns will be from different sides of a join, and that will make it a join condition. And if it's column equals expression, where the expression uses the value of other columns, again that's going to be a join condition. But it might be an expression that results in a literal, in which case that can be pushed down to the indexes. usually. So then another type of expression that can be pushed down is the same as above, but or column is null. So column equals something, or the column is null. And then also we can push down column is null or column is not null types of expressions, so that they can affect the joins that that those nulls come from, or in other ways the nullability of columns in tables that are being accessed. The kinds of operators that we can push down in this way is equals, like we've used in those examples, but also not equals and the other inequality operators. We also have a universally quantified not equals. That's kind of equivalent to SQL not in or Sparkle not in. We also have range operators that work on a less than and a greater than. And for Sparkle, we have same term operators, and they can also be pushed down through the plan. So in addition to pushing down those filters, we can also mutate and modify some of those filter expressions. And the aim here is to take a more complicated expression and turn it into one that we can push down. So one thing we can do is that using static type information, that's information we know that maybe comes from, this column is a string and this column is an integer. If we have that kind of static type information, we can look for casts in the expressions, and we can remove casts when they're essentially a no-op, given our knowledge of the types. Another thing we can do is we can know the nullability of columns, whether they could contain nulls or not. And when there are tests to say that it either must be null or it can't be null, we can make modifications to expressions. So for instance, if the expression is column is null, and we know that that column never contains nulls, then we can turn that into a false. So another kind of optimization we do is common clause extraction. So if we have, as you can see here, an expression of the form A and B or A and C, then we can extract the A and turn that into A and B or C. Now the reason to do that is, if you recall, I said that we could split the clauses up at the top level and, but we can't do that with a top level or. So this optimization aims to put clauses at the top level connected with an and, so that we can split at least one of those clauses out and potentially push that down to indexes. And the final type of optimization we do here is if you have column equals A or column equals B. Again, the or is a problem. We can't push that down and we can't split the clauses on it, but we can turn that particular formulation into column in A comma B. And so we do that in order to be able to push the in down to the indexes. There's two other optimizations we do due to the syntaxes that SQL and Sparkle use for semi-join and anti-join. Now, semi-join in this case is an in with a subselect, or a filter exists in Sparkle, and an anti-join is not in with a subselect in SQL, or a not exists in Sparkle. And what we can do is we can find those filter expressions and turn those into the join equivalents in a lot of cases. And the join equivalents are a lot more efficient than the filter expressions themselves. So that's a positive improvement to the plan. So after static optimization, we'll move on to heuristic optimization. Remember, this is applying rules of thumb, things that are generally true. So some of the things that we'll do during heuristic optimization are we'll determine simple join orders for series of joins. We'll rearrange them into an order that probably makes sense, or that's probably more efficient to the one in which they're written. So that's based on estimates of the number of rows returned there and the cardinality of the columns. That is used to estimate the result of joins. We'll also choose a join algorithm for each join based on local analysis of the cost. Local analysis here means we're just really taking into consideration this little subsection of the plan, and we're ignoring the wider plan that's around it that might mean we would make a bigger decision. But that wider context is looked at later under the cost-based optimization. As well as that, we'll determine the permutation or the sort order that we access the triple index under. And if you're interested in permutations and methods of accessing the triple index, then you might want to go and look at the fourth section of this deep dive, where we start to talk about the triple index and how it's stored, and the fifth section where we talk about how it's queried. So heuristic optimization, you can actually just use heuristic optimization if you're using MarkLogic by using the optimize equals 0 parameter to either XDMP SQL or to SEM Sparkle. Now that is a much quicker optimization, but it's often less effective. But what you find is if you've got a very small query plan, usually that means a very small query, then optimize equals 0 may do just as good a job as a longer lasting optimize. Additionally, you'll recall that we cache query plans, and so usually it makes sense for us to spend a bit longer optimizing and cache it and use it over and over again. And what we do, what we're relying on there is what's called amortizing the cost of optimization. We're spreading it out over multiple executions because it's cached. Now, if you're only executing your query once, it may not be worth the time spent optimizing. It may be quicker in total to optimize less and get on with executing straight away. So in some cases where you're evaluating very small queries or queries only once and not in a repeated fashion, it may make sense to use optimize equals 0. Now, if you're using higher optimization levels, you're using cost-based optimization. And this uses an algorithm called simulated annealing. Simulated annealing is a process, a guided randomized search for a good query plan. At each stage of the algorithm, we apply a very small change to the query plan called a mutation. The criteria for a mutation is that it gives the same answer before and after the mutation has been applied. Having applied that, we look at the cost and we say, did this improve the cost? Did it make it smaller or not? And if it makes it smaller, we accept that change and we keep it. And if it doesn't make it smaller, there's a random probability that it gets accepted or not. And the reason for that can be looked at, can be understood when you look at that graph, the white graph here. It's not a straight downhill slope to the best query plan. Sometimes you have to accept worse query plans as an intermediate step, a slight uphill, before you find a bigger downhill on the other side. In other words, a query plan that's a lot better. And those local minima, the little valleys that aren't at the bottom of the hill, they need a process to kind of make sure that the query plan gets out of those and actually finds a good query plan that's even lower cost. So the inputs to simulated annealing are the list of mutations that can be applied and a cost function, and the cost function determines whether this plan is better or worse. So let's look at the kind of mutations that we have that the optimizer can apply in these cases. So we've got a choice between triple permutations. I've mentioned that a few times, And we might choose some triple permutations because of the access patterns that allow us, that permutation allows us in the triple index. We may be able to read less of the triple index if we choose a certain permutation. In addition, we may have a desired ordering that we wish to get from the triple index, and the cost function will track sort orders returned from subtrees of the plan, and will obviously reward sub orderings that are required by the query, potentially by an order by, or by a group by, or by a sort merge join. So in those cases, we may choose a permutation that has a higher access cost because it allows us to get a certain sort order, and that allows us to avoid a brute force sort later on. Now with lexicon access, we've got a choice of ordering there as well, either value order or fragment ID order, and those are good for, well, value order is good for value joins or for value sorts, and fragment ID order is good for joins on the fragment ID. Now with template view access, that's the row accessor. When we access that by row or by column, that's a choice as to whether we read all of the values in a row before we read all the values of the next row, or if we're only selecting a very small number of those columns for each row, we might choose to access column by column by column. And we can also choose to access tables sorted by a column as well, and indeed restricted by a column. If you look at the fifth part of this series, where we talk about triple index queries, we'll go into what that looks like and how that works. So some other choices that we've got, mutations that are available, are the choice of physical operator for a join, and we looked at some of those in the first section of this deep dive. But we've got things like a hash join or a sort merge join, scatter join, and all of those kind of possibilities that are available for the physical operator. We've also got join rearrangement mutations. So those are things that take advantage of the commutativity of joins or the associativity of joins, so they can swap the order of the arguments, or they can rearrange the arguments in two joins, one of which is the child of the other. We have some bind mutations. So bind is evaluating expressions and assigning that value to a column, and we can also push down and pull back bind operations. Now the reason to do that is by pushing down, that is pushing towards the leaves of the query plan, or by pulling back, that's bringing it back towards the root. We might be able to execute the bind expression fewer times, because there may be fewer rows by pushing it down, or there may be fewer rows by pulling it back because it's back past a filter that's removed rows. So, and obviously evaluating expressions fewer times is going to be better for our final runtime. And then there's the grouping operator as well. There is both a sort implementation and a hash-based implementation there. So making a decision about which one we use is important there. Now, with some experience of simulated annealing, we've found that the number of mutations is actually quite important, because what we have with simulated annealing is we only have a fixed time to investigate the possible query plans, and if there are too many mutations, there's too much to investigate, and we don't end up doing a very thorough job of it. So as I said, if we've got too many mutations, that might mean too little optimization time as well. That's another way of saying it, and that results in poor query plans. So when we're optimizing, we also reduce the mutations that we consider, potentially. Now that depends on how big the list of mutations is, but we do things like track interesting sort orders. So if there's an order by, we keep a note of the fact that we want to be ordered by this column. And then deeper into the plan, if we find an index access that might be able to return in that sort order, we'll add a mutation to let it do that. But otherwise, we don't add the mutation to change the sort order if it's not actually required by something further up the plan. Another thing we do is we track the scatter conditions. If you recall, when a scatter join takes information from the left-hand side and passes it into the right-hand side to restrict query execution, that can result in a smaller right-hand side and a more efficient query execution. So we track that in the cost function, and we track that when we're adding mutations, and we add mutations that facilitate a smaller query plan retrieval. And we don't add mutations that don't do that. So the other thing then is after that, when we've got a mutation list, we then still prune it, and mutations are given an importance. And this is kind of a fallback position, but if your mutation list is so big and the time is so small, those things will happen at lower optimization levels, and they'll happen with bigger queries. We want to concentrate on the mutations that will maybe have the biggest impact on the final execution time. So mutations are given an importance, and the lower importance mutations are pruned off to make sure that we thoroughly explore the more important mutations when we're optimizing. An example of this is that at optimize equals 1, optimize level 1, the bind operators push and pull mutations are always pruned. And it's only at higher optimization levels that we'll explore the possible benefits of pushing down bind operations to potentially make them more efficient. So let's talk about the cost function, and this is the other core part of cost-based optimization. When we calculate the cost function, we have several different inputs that help us to actually determine what's going to happen. So there are triple index statistics. They are pre-calculated when the index is made or when it's merged. And we fetch those according to the kinds of triple index accesses we're going to do. There's lexicon statistics that are calculated when at optimization time. Some of these statistics include things like numbers of results that will be returned, and also what we call the cardinality of columns. That is the number of unique values in those columns. That information is helpful for determining the result of joins later on in the plan. We also gather some cluster statistics. So we want to know how many dnodes there are attached to this database, how many stands those dnodes have, what kind of memory conditions they have, and we go out and gather that information and use that as input to the cost function. And also we have a number of things that we measure in the cost function. So we will measure CPU time effectively, both on the E node and the D node, because we have things that are executing on both places. We will measure the amount of network that we're using, how big the messages are that we're sending over the network. We'll measure disk I/O on the D nodes and how much we need to pull up off of disk. We keep track also of peak memory usage, both on the E node and the D nodes. It's important not to run out of memory. In fact, memory is distinct and different to CPU, because if you run out of memory, then the operating system gets most unhappy and your program ends up being killed or stops working. Whereas CPU, you can always use more CPU. You can't always use more memory. We also keep track of the row count, the number of rows returned from each operator or predicted to be returned from each operator, and then column cardinalities, which is I did explain just now. So if you use the optic statistics trace flag, you will see output like this XML in your logs. And this output contains information, that information that gets gathered for input to the cost function. So you'll see a total count of rows, and you'll see unique subjects, for instance, on some of the triple index access statistics here. You'll also see an entry here for the view that's being accessed and the number of rows that has. That's the view there, just highlighted in green. And that one there is statistics for the PFLT literal that gets used in the filter. That PFLT is the object member of a triple, and we can tell how often that occurs in the database, and therefore we tell how effective that filter clause is going to be. This is the cluster statistics that you'll see reported in the logs if you use the optic statistics trace flag. Here you can see I was obviously executing this on a single node cluster, so hosts is 1, stands is 2, and you can see an estimate, well not an estimate, you can see the amount of memory assigned and available to query execution in both those kind of capacities. As well as the different things that we measure, we have different types of costs. So we have asynchronous costs. When we start executing our query plan, usually we'll send messages across the dnodes, tell the dnodes to start their execution. Or we will start some asynchronous disk I/O if we're a dnode ourselves. Those kind of asynchronous things happen in the background, and so we track those costs separately, that end-to-end time can be only the maximum of those costs rather than the sum of those costs. We also have upfront costs. Those are things like building hash tables. If we have to build a hash table for a hash join, then the table needs to be built in its entirety before we can really return any results from the query. Okay, so upfront costs, start costs, need to happen before any results come back. Then we have a cost per result row streams. Those are called proportional costs. And those costs, let's say you only take 10 of the results because you have limit 10, out of 100, then you can take 10 hundredths of the proportional cost and discard the rest, because it's actually not going to pay. You don't have to pay for the rest of the results to be calculated. And then in an orthogonal direction, we also have both parallel costs and serial costs. And parallel costs is a measure of the time to finish. Okay, you start, and when you get your finished results, that's the parallel costs. And serial costs, that's a measure of the total cluster resources that are being used by this query. Because things might be happening asynchronously, they may be happening in different threads, but it's important to measure that as well, because we want to be good citizens of the MarkLogic ecosystem, and in MarkLogic we expect there to be more than one query executing at any time. And so we don't want to choose a query that is marginally faster at the expense of using up all the system resources and crowding out anything else that might be trying to execute. So all of those things together results in this matrix view of the cost of a query. And the rows are the different things that we measure: CPU, DCPU, network, and I/O. And the columns are the the things that we're measuring. So you can see there the parallel columns. They've got parallel async, parallel start, parallel proportional. Okay, but with serial, you just have serial start and serial proportional. because the async, obviously with serial, we're measuring total system resources and we're not discounting anything because it runs in parallel. So we don't need to have a separate category for asynchronous execution. So here you can see all the numbers filled in for a query that I executed. Now if you use the optic optimization trace flag, in the logs you'll get some output that looks like this. And this output is telling you all of the numbers from that matrix as well as a few others there. So the first line here, M, that's the most important number. That's the final cost or metric, which is a combination of all the other numbers. On the next line, IO, that's the IO row, and the slashes separate the values between all of those columns that we just saw in the table. So then we have network, CPU, and dnode CPU measures. The next line is a measure of the total of the peak memory usage on both the enode and the dnode. And C is the count, the estimated final count for the query. And the last line there contains cardinalities of each of the columns from the query. At the end of the cost function, those cardinalities aren't very useful. They're used for estimating the joins and how many results are going to come back from those joins. So when we want to get the final number that we actually consider to be the cost, we combine all of that matrix of information together. The final metric, first of all, it adds up the various rows, and the CPU, DCPU, IO, and network, and times those by factors or weights according to what's been programmed into the system. There's also a latency factor and a throughput factor. So latency is time to first result in effect, or time to last result. So end-to-end time that equates to the parallel measure that we talked about. And throughput factor is the amount of queries in the whole system can handle, or the serial measure, the amount of cluster resources that are being used. Then we take memory, and memory, because of that, what I described earlier about the way that if you run out of memory, there's no more memory to use. You can't just keep using more memory. So memory is added as a multiplying factor to the cost. It's treated as a proportion of a quarter of the available memory for query execution. So the query optimizer is always aiming to only use up a quarter of that memory. It won't always succeed, but depending on the query, but that's what its aim is. And we use a cubed function for that as well, so that it rises sharply after it exceeds that quarter proportion, and the cost optimizer therefore spends more time trying to reduce the memory that it's using than on other types of optimizations. Now, I mentioned this in the previous section, but there is a query plan viewer that you can use to visualize these query plans that we've been looking at. And it's worth going to check that out. The URL's on the screen there. It's a GitHub repository. And if you hover over the operators in this, in recent versions of MarkLogic, the cost function output is actually embedded in the query plan. So you can see those for each operator. When you hover over it, you can see the costs that it was assigned when the cost function was run on it. So let's just recap what we've learned. We've learned how to write filter expressions that can be pushed down. We've learned about optimize equals 0, and that we can use that for small and or one-off queries potentially and make that faster. We've learned about higher optimization levels. Higher optimization levels, even than 1, give us more time to spend doing parallel do simulated annealing, and therefore give us the opportunity to find better query plans, potentially. We've learned about the simulated annealing algorithm and how it uses mutations and a cost function to find a better query plan. We've looked at the statistics that are the inputs to the cost function, and really that's the optimizer's view of the data. If something isn't in the statistics, then the optimizer is unlikely to make a good decision about it. And hopefully this will give us a good foundation for understanding efficient query execution. So do look up part 3 of this deep dive, which does talk in much greater depth about looking for the causes of inefficiency in query execution. Thank you very much for your time.